It's a great pleasure and a privilege to have Dr. Paul Dayton join us this morning. Paul is a professor here at Scripps Institution of Oceanography and Biological Oceanography. He came here in 1970, straight out of graduate school from the University of Washington in Seattle. Paul is a very esteemed scientist, although a modest one, I must say. He didn't want me to say all this, but I'm going to say it anyway. He is the author of some 120 papers, and to his credit, he is also the co-author on the recently published Pew Oceans Commission report on the ecological effects of fishing. And Paul's research interests have spanned a great number of marine environments, from the Arctic to the temperate oceans to coastal marine habitats such as the Great Barrier Reef, and also habitats in the Antarctic. The main focus of his career, however, has been the kelp forest right here offshore in Point Loma kelp forest, but he's worked on many other kelp forest habitats as well. Now, Paul, again, is quite modest, but I have to say, in addition to his really impressive publication record, is notable because he has actually won... Sorry, Paul. I do this to everyone, and I have to say, I'm always so impressed with the people here at Scripps. Whenever I give these introductions, I just think, wow, there is no other place on this planet where you have such a collection of scientists, and Paul is certainly a premier scientist here at Scripps. But he's won both of the major research awards given by the Ecological Society of America. He's a fellow of the American Association for the Advancement of Science, and was recently recognized by the American Association of Underwater Science with a Lifetime Achievement Award. So it really is a privilege to welcome Paul today, and he's going to speak on the ecological costs of fishing, and he'll offer his perspectives of how oceanography as a science can help improve our understanding of oceanic ecosystems. So apologies for the accolades, Paul, but welcome.
The published rendition looked like it was going to be another one of my discussions of fishing impacts, but I think at this point we all of us anyway, have heard and realized that the baselines have slugged. Conditions are bad. If we're going to fix them, most of the solutions will be found in politics, and so there are issues of governance, which I don't have any knowledge of. But the Pew Oceans report that just came out, I think gives a very good detailed blueprint for some suggestions for improving their governance of our seas. So I thought that rather than talk about something governance that I don't know anything about, or rather than talking about the same old straw of the world is in decline and isn't it awful, that I would give you my very personal, and I'm saying this just from me, I'm thinking more about my grandchildren and things than Scripps where I work, but I don't represent. And so it's a personal idea of some of the things that we really need to deal with if we're going to, as scientists, if we want to understand how the oceans work. And you've heard of ecosystem management. Well, we don't manage ecosystems, they're too big. You manage humans with an ecosystem perspective. And so how do we understand the ecosystems if we're going to have this perspective of these oceans? That's what I would like to try to talk about. And I'm very much out of the shallow water that I live in. I'll talk for just a few minutes on the kelp system, which is my comfort zone, just to give you an idea of what I'm talking about with ecosystem relationships. Then I would like to slide into, well, I'll talk briefly about scaling issues. Then I'll talk about pelagic ecosystems that I have never studied. So let's hope for the best, and let me wander through this. I've got this slide was made up, but and it's just talking about factors that destabilize kelp forests. We have a lot of sort of physical things, but the ecosystem has to do with biological interactions, how one population affects the other. If you affect a population, does anybody else in the community care? And just really quickly then, we have little fish, which I'll just refer to as canopy fish, the Senioritas, Brachiosteus, small little fish that are up in the canopy that most people don't recognize. And they actually have a surprisingly important role in maintaining the kelp forest, because the kelp forest is a substratum for all sorts of things to settle on it. And if these guys aren't chewing it off, like you see the bite marks, then the things that settle on them escape and they sink the kelp plants. And in some cases, this was in Chile, they sink entire kelp forests. So these little people are important players, and that's the type of thing I want to talk about. The same thing, they disappear, the little fish disappear during El Niños for various reasons, and when they disappear during an El Niño, the El Niño breaks, the kelp plants recover really quickly. So the next thing after a big El Niño in the kelp forest is a big boom of kelp recovery, and then it'll disappear. And the reason it's disappearing is that those little fish are gone, and amphipods that are natural parts of the community come up off the bottom and they eat the kelp bed. So you have this big sort of collapse, then the fish come back, they eat the amphipods, and we get going. The other big biological destabilizing effect for kelp forests, as you probably know, are sea urchins, which overgraze kelp forest around the world. And in almost every case, probably in every case that I've seen it, I can sort of in my mind imagine destabilizing things in the biology that result in these urchin barrens. In our case, the urchins do overgraze the forest, but we have an interesting situation in that the red urchin, which is one of the urchins that's fished, it's the urchin that's fished, is also an important nursery ground for the recruitment of a whole lot of things. Especially other urchins and abalones, back when we had abalones. So when you take out the red urchin, you eliminate an important nursery. It doesn't eliminate the recruitment of these things because they still find a few places to settle, but it's almost an order of magnitude difference back when we had them. That's another biological interaction. Another thing that might affect the urchin release are abalones. This is a picture of black abalones in the Channel Islands. But 100 years ago, hard hat divers, were taking as much as 2 tons of abalones per dive. And everybody talked about the hard bottom in Southern California being just pavements of abalones. And around the world, when this happens, and abalone fisheries come in New Zealand, Australia, and South Africa, the abalone fishery is quickly followed by an urchin outbreak. It's probably just competition for space. Finally, we have the urchin predators. The sheephead have been gone, as you know, for a long time. I mean, the sea otters. But then we have a sheephead, and especially the big lobsters, are really important predators. They're very powerful animals, and they used to be able to eat everything. Then the male sheephead are fairly easy targets for spear fishermen. But mainly the problem with the small fish in the kelp forest is the live fish industry, a trap and a hook and line fishery that has just more or less eliminated the sheephead and a lot of the other smaller fish. They're not extinct, but they're much reduced. Then we used to have a lot of those big abalones. That's Jim Stewart, with some that he caught in the 50s. Early in the century, the dates are sort of confusing, but I've seen pictures from the 30s of the Chesapeake Bay fishing cannery, with guys knee deep and hip deep in lobsters, shuffling them into big vats. And we used to have a lot of lobsters. This is a day's catch, being processed and shoveled off and wheelbarrowed in. So we still have a lobster fishery. The lobsters are okay, but we now have important players in the ecosystem that are at least much changed. That's really all I'm trying to get at here. Finally, we had these monstrous fish, and they were very abundant. For almost 50 years, sports fishermen took a lot of them, and commercial fishermen did as well. I don't really know what they did because we haven't seen one in our study zones in Point Loma over 30,000 some odd dives. They're not extinct. They're coming back in this little reserve. But I don't know what role they had, but they were bottom feeders. They probably ate, maybe they ate the lobsters. They probably ate the small sheephead. So they were probably players, but we really can't reconstruct that. So we talk about the ghost forest, and you've heard about that, and it is impossible to reconstruct an ecosystem from old photographs and things. But at least you've seen that these biological interactions are really quite important at maintaining the system vitality. So the other thing then, as I want to shift out into the blue water, into the oceans that I don't know much about, is that it's really important to recognize scaling. This is what we call a stomal diagram. It's a log thing, so it's a huge difference. This is time and this is space. And the point I want to make is that when you really start to get to important events in the ocean systems, they're usually at larger scales. The diurnal vertical migration is sort of at the 1-day scale. Tidal components, there's a lot of sort of physically driven, and then the vertical migration, which I'll talk about. Otherwise, we're looking at really pretty big scales, like decades to hundreds, to mesoscale, hundreds of kilometers and more, before you start to see really important things. Now, the problem that this poses for scientists is that it's in these tiny scales that are easiest to study. I mean, you can do it in the lab in many cases. You can go out and take a snapshot and then bring it back. So a lot of the energy that goes into oceanography is on the really fairly small scale things, when really where the ecosystem counts is on these really bigger scales. And it's important to remember that scaling is just terrifically important in the ocean. You know about kelp coffee, I hope, but this is just an example. These are sardines and anchovies, and this is a recent cruise. The only point I want to make here is that, you know, if you don't have a big scale in your study, you might miss the entire picture. You could be, the normal kelp coffee cruises are down here, and look, all the sardine recruitment is up there. So you've got to have a really good sized scale to have a picture of what's really going on at the oceanic perspective. Now, you've also heard about kelp coffee in the time series. It's really one of the only excellent time series programs in the world. And this shows you the regime shifts, what they call the PDO, the Pacific Decadal Oscillation, and that these are events that are poorly understood. I certainly don't understand them, but they work across sort of 10 to 15 year scales, and they're big changes. They permeate all through the system, and so if you don't have that perspective, and if you do your research right here, you really are missing out on a lot of information about how the world works. This is a regime shift. I'll talk about it, in the future a little bit. The only thing I'll point out too is that I just borrowed this slide from Mark Ullman, but that he picked out 2 salps, jellies. I'll come back to these jellies because people don't think about jellies, but I think that they're important in ecosystems, and it's important to keep track of them. Okay, now here you have another cartoon. This one I took out of Daniel Pauly's book. He's a good modeler and a fairly poor biologist, but and that the picture doesn't really represent reality. He's making the argument that as you take out all the top animals, which he's demonstrated has happened, the big guys, then the little guys that they used to feed on will have a population explosion, and then the big guys then the fishery will re-gear and knock those guys down, and then their prey will explode. Meanwhile, the big guys at the top get their heads knocked off whenever they show up. So he calls it fishing down the food web, and this diagram makes that point. The problem is that the biology in the diagram is a little funny because he's got the fish really thoroughly mixed up. There's no squid, which is really important, but it is a useful sort of picture of what's going on. There's 2 other things that I want to point out that he's picked up. I think all these little blips are the really small copepods, euphausiids, the types of things that people sort of study, and there's no connection between these little blips and the fish, and that's a point. That's correct. That's a point I want to make. There are connections, but we just don't understand them, and they're terribly important connections. The other thing is that he has it ending in jellyfish, and this is sort of ironic because he got that one right, and I'll come back to that again. Okay, so let me just jump into the Bering Sea and jump into waters that are over my head. Most of you know about the Bering Sea. It's full of really neat animals, all sorts of birds, whales, seals and walrus and the belugas. These are bowheads. So it's a neat place, but it's a sea. It's one of the most productive, it may be the most productive ocean in the world, and it's very heavily fished, and there's a lot of controversy. It also used to have whales. I'll come back to this. I put this picture in, I made the sort of collage to show you that animals, the big whales, and a lot of other animals we'll see, have to aggregate their prey in order to be able to eat them. So the big whales can't just sort of skim along. They have to have aggregations of prey, and they have all sorts of behavioral adaptations to do that. That's why the humpbacks have those big white arms, I think. They flash them, and the mice just immediately respond with a startle reflex, ball up, and then they eat them. But then they work as a group. They'll make bubble nets, and then other guys will come up the bubble net, and you can see they have a pretty good sized mouth. So these guys have a lot of, and that's true, I think, with different tactics for all of the great whales, the big baleen whales. They've got a lot of tactics to aggregate their prey. They were important players. They ate a lot. This is just a diagram. Don't follow it. Don't get too worked up on it. It's confusing, but just listen to me. This is the right whales that got tanked in the turn of the century. The main point I want to make is that we had a lot of whaling that took out a lot of these big whales, and that whaling was in the 50s and 60s in the Bering Sea. And the other point that I make is that a lot of things are coming down, crashing, and going up. There's a lot going on. There's a big regime shift that really sort of switched from herring to pollock and to crabs to something else we don't know because the crab fishermen took them all. And then finally, the stellar sea lions collapsed. And they were noticed, and they're now endangered. And that's caused a huge ruckus worth many millions of dollars. $43 million last year, I think it was last year, alone that Senator Stevens sort of dumped into Alaska to prove that the pollock fishery, which is a huge fishery, isn't responsible for taking the food for the stellar sea lions. And so there's this big issue. Why did the stellar sea lions collapse? What's going on with the herring, which are sort of gone, the pollock, which are in big numbers, and yet the stellars are down. And one hypothesis that's come up recently relates to the orcas, the killer whales, that actually, they used to eat a lot of these big guys, and the argument goes is that, well, when these guys disappeared, they switched over and knocked off the stellar sea lions, and then they went and took otters and other things. So that's the orca top-down argument. And it's got some problems because meanwhile the gray whales, which aren't in this picture, were expanding exponentially just while the orca were so hungry. The gray whales come through Umiak Pass, which is sort of a conveyor belt of food. So all the orcas had to do, is sit up there and eat all the gray whales, and they didn't. They didn't eat the fur seals. So that hypothesis is oversimplified. But also, so is the pollock food limitation hypothesis. We really don't know. And if we'd had a Cal Coffee program in the Bering that really looked at how the ecosystem works, we probably wouldn't have this problem. I bet we'd have a pretty clear understanding. But here you have Danielle Pauly's ecosystem model, and you'll see again it's really short on biology. Basically, it's smoke and mirrors, but it's pretty good smoke and mirrors because the dots are the data points. And the lines are where you have some idea independently of what was going on. And there's some semblance of his dots, but there's a very little biology in there. Other approaches to understanding it are these food webs that you find published. We can count the air breathers. They come up to breathe. People love them. You count them, both out on the inner shelf and on the outer shelf. And we sort of know what they eat because you kill them and you find out what's in their stomach. So you can draw these lines down to the gaddids, the sand lances, the euphausids, and here's the pollock, which everybody fishes. But these boxes down here are virtually unknown. And I would like to argue that this is where the ecosystem has to be studied. We know a lot about these. We know a lot about the climate effects on fishing and on the top order things. We just know virtually nothing about the interactions about these guys down near the bottom. And there's no connection of these guys to what they eat, the copepods. You never see that. So getting your ecosystem from copepods to whales, or even from copepods to just the fish this big, is a real challenge that nobody's addressing. Now, I promised you the jellyfish, because in the Arctic, the jellyfish are a really interesting issue. These pictures are not the Arctic ones. I don't have Arctic pictures. I took this in the Monterey Bay Aquarium, and these are my own pictures from the Antarctic. But the point I want to make is that we never think of jellyfish, but they're very important potential players. This guy had tentacles that were 50 feet long, and they were fairly common jellyfish drifting by, and as they drift by, those tentacles are killing things in an area the size of a house. They have almost no metabolic rate, so they're not spending any energy to feed. This guy's tentacles were 100 feet long. And so these guys are predators. The little ones are predators. You get a high density of jellyfish, they're getting everything. We know that from the Black Sea, where a jellyfish that I wouldn't have thought was such an important player was. It stripped the Black Sea of everything. It was an introduced ctenophore. But so jellies are important, okay, and they're usually ignored, but not in the Arctic anymore, because this is an older figure, but it's still continuing up here someplace. They're catching in their trawls something in the order of 250,000 metric tons of jellyfish, and those guys are important predators. There's a paper that calculates that these guys are probably taking something like their whales may have been taking. They're very important players in this system, and they didn't used to be there. And the research, the one paper that I know about, makes the argument that this is a food web consequence, like Daniel Pauly's cartoon that ends up in the jellyfish, that you take out all the pollock and then the jellyfish are released from competition. I actually don't believe that, because they haven't taken out all the pollock. There's a lot of pollock, there's a lot of things there. I think that there's another explanation, and you find it in just old-fashioned textbook natural history. Pelagic jellyfish sometimes reproduce entirely at sea, but the species that live in the Arctic have a benthic phase. So the males and females release eggs and sperm, they make a larvae, the larvae goes to the bottom, okay? Now it settles on the bottom, it feeds down there, and it turns into a jellyfish machine, budding off jellyfish, thousands of them. When it runs out of energy, the last upside down jellyfish that was about to bud off feeds until it has a lot more energy, and it does a few more thousand, and it continues. So when the mother and father jellyfish produce that baby that settles on the bottom, in the good old days they settled on anemones and sponges and soft corals. These were my pictures that I took in the Bering in the early 70s. So the bottom had that sort of stuff, and these guys damn well eat those things, so they don't have a chance to settle. Now you've got trawlers, and this is a really old cartoon map. The trawlers are now all over the place. So the trawlers are wiping out all those sponges and jellyfish, sponges and anemones and things, freeing up the bottom for all those larvae. Now you've got all those little jellyfish machines all over the place, and this is going to continue probably. And eventually you're going to get a regime shift dominated by jellyfish. And so again, this is the type of thing, just old-fashioned natural history and sort of big picture things that you need to look at. So just summarizing, there's an urgent need to really understand these guys, the sort of the middle level parts of the ecosystem. We don't know much about their biology. We know something about them, of course, but we need a lot more. And we need, especially in the Bering where it's shallow, you need to construct the benthic pelagic coupling. You need to hook the bottom into the water column above it. Okay. So now let me switch to the Antarctic. Lisa Balance, who works at NIMS. Lisa has summarized, and she gave me the overheads. Basically, Lisa's asking this age-old question of what happens when we take 2 million whales from the southern hemisphere. Well, that frees up immediately at least 150 million tons of krill. And then there's all sorts of things that could happen to that krill. Now, people realize this, so there has been research on the krill. There's been a lot of research on the krill, and a lot of things respond. So we take out the giant whales. One of the things that happens is these small whales, these minke whales, have very much increased their population. And the giant whales had to have that food concentrated. I explained that to you before. The minke whales don't. They're skimmers. They're smaller. They don't have to get the big units. But if you have more minke whales that are skimmers, and you have a krill fishery taking the patches that they can see from satellites, you don't have any patches anymore. You have fairly serious competition in all these other guys that have responded to the krill. You have a really, probably a fairly major ecosystem change, and it'll be hard for these guys to come back because they have to have big patches of krill. Let me just back up and talk a minute about the first fur seals. They were fished down in 1805. They basically cooked the last fur seal and skinned it, and it took them a long time to recover. It wasn't until they knocked down the whales that the fur seals recovered. And have they recovered? There's probably many times more fur seals than there ever were before. They've wiped out much of the terrestrial habitats that people are trying to protect. Say in Signy Island, the British have reserves to protect very rare subantarctic plants. All those things got bulldozed by these fur seals. There are tons of fur seals down there. And on the next picture I have some penguins. We don't have very good before data on the emperors, but the emperors are squid eaters, and they're certainly players in this game. But the king penguins are very clear players, and there are millions more king penguins than they used to be. Jerry Koyman took this picture, and that colony hadn't even been there 2 or 3 years earlier, and there's probably 1 million birds that just came in between his visits. So when you take out the giant whales in the 60s, all sorts of things happen through the ecosystem. And the crab-eater seals. 80% of all the seals in the world are crab-eater seals. They're specialists on krill. There's just tons of crab-eater seals. There's just immediate ecosystem responses to the taking out of the whales. Again, the same sort of thing. You have all the animals that people count, the birds. And then you have these guys that nobody knows anything about. You know the gut contents, so you say, well, the emperors are squid eaters, so we'll put squid in there someplace. We'll make tophids, they eat myctophids. But very few people really study these things. And this, I think, again, is where the action is. And the action is getting the copepods and the primary production into the krill and into these guys. And interestingly, in the Antarctic as well, we now have a salt bloom. The jellies are on the scene again. And the scientists relate the salt bloom there to changes in the ice cover. As the ice erodes in global warming, the salps are replacing a bunch of things. The ecosystem is going to get much poorer. I think that their correlation is true, but I think there's a lot more ecosystem dynamics that are going into the salt bloom as well. So if we remove the large whales, the fur seals, the penguins, all these things that Lisa Balance is worrying about, basically have shifted the system. And so these are big ecosystem shifts, and the dynamics of the ecosystem shifts, I think, are fairly poorly known. So in the Antarctic, you have the squid, again, always the squid, the ice seals, the Keller whales and leopard seals. They're the wild cards. The leopard seals eat some of the seals. The killer whales eat everything. So you've got this system in turmoil, and it's again being fairly well studied. It's ironic that the research that's done on these scales, on these questions, is done by the National Marine Fisheries Service. Most of the, not all, but much of the research in both the Arctic and the Antarctic and the mid-Pacific is done by NIMS. Okay, this is something that's been in the press recently. This is just a graph of the big fishes, and the fish differ, but they're the swordfish, the sailfish, the big tunas, the bluefin tunas, and almost all of the fisheries in the world. And the figure that was out in the press is 91% of these magnificent fish have been removed. And people quibble. You'll hear them quibbling. Well, it's not really 91%. It's 87. But really, the fishery management plan for the few fish like our yellowfin tuna that are fairly well managed, the management plans themselves strive to take 70 to 80% of the fish. I mean, so they know that they're taking a lot of them. Our yellowfin tuna, something like 900 million pounds are taken every year. So what does that do to the rest of the ecosystem? These are the top predators. Now I'm shifting out to the blue water Pacific where I really don't know anything. And again, you have these big predators. They have to concentrate their prey. And so concentrating the prey is what the game's all about. They flash, the sailfish swim around, and herd their prey. They have their sails up. They flash like neon lights. And the marlins flash. They're gorgeous, dynamic animals. And they really did a job on herding the prey up. Now, where are the prey? How do they find them? The prey are actually hiding from these guys. The prey go down below the thermocline, maybe into the oxygen minimum zone, where these guys can't go, where it's dark. They're visual predators, and they hide down there where it's cool. And then when it gets dark and their eyes don't work so well, then those guys all come up and eat. And that's when they get herded. They get herded by the dolphins with their sonar. They get herded by the people that can see them. But the herding is really important. And what are those guys that are down there that they eat? Well, here we are again. They're squid. There's squid all over the place. And they're very poorly studied. They're hard to study. There's one guy in Hawaii that studies them. There's some museum people, not many. They're very poorly known. How about the fish? I mean, there's pomfrets, there's a bunch of herring-like fish, and the squid get maybe up to Humboldt squid. They get pretty big, and all those fish and squid are important players in their own right. They do things. They're really good predators, but they get herded up. They get herded up against the roof, and when they're up against the roof, then it's easy to forage on them because you can just sort of shoot through the roof and get them, and you get pictures like this. Here you have a yellowfin tuna airborne with a bunch of petrels and what's going on is that the squid are all up against the tuna are herding them up, the birds are feeding on them, the dolphins are feeding on them. You've got this big wad of squid, and there's 10 species of birds that absolutely depend on this herding to bring their feed up. I think of them as conveyor systems because the birds can't dive down to the thermocline. These guys have to convey the fish up and the squid up for the birds to eat. And basically a lot of those birds are specialized on squid. It's the squid that we don't know much about. And in fact, it's so important that there's 10 species of seabirds that have a name, the subpredator dependent guild. Their entire life depends on these big fish chasing the things up for them to eat. You take out 91% of those big fish, and you start to see consequences that you might not have thought about. This is some stuff that one of my students did, tagging other albatross. And again, they're flying fish consumers and squid consumers, and they nest in Tern Island and central Hawaii. And the males and females will fly a hell of a long ways to forage on predictable areas where they can count on getting food brought up to the surface. The other one, the Laysan albatross, goes up into these areas. Well, these areas are known to be hot fishing spots. In fact, they're frontal zones, and the catch per unit effort area is very high. This is where the fishermen go. Again, you've got a lot of action. The birds, and there's some 50 species of albatross that are fishing these frontal zones, and are probably relating to things that are flushing the prey up to the roof. These guys are good oceanographers. The birds are. They can see the frontal zones. They go right to them and they forage there, but they depend on things underneath to get the food up. So these conveyor systems are really probably important to certainly those 10 species and maybe all the 50 species. And then finally, as you probably have heard, the longline fisheries are just taking a huge impact on these birds as incidental catch. The birds get the bait as they're thrown overboard, and some colonies of birds have been taken down, and these are long-lived birds, 75 to 100-year-old birds, that are being taken down as much as 50 to some of the British work in the southern seas is 90%, just from incidental catch. So a lot of things are going on out there, and we still got that same suite of species. In this case, the pomfrets, the fish, the herring-like fish, all those squid that nobody really knows, and they are sort of the engines of the system, and they're virtually unstudied. Well, some people that do study them very efficiently are beaked whales. Now, we don't know much about the beaked whales. There are 20 species of them. We keep finding new species even. They're deep divers. They don't herd their prey. They have very sensitive hearing because these are the ones that are killed by sonars. The acoustics experts don't hear them at sea. My guess is that they're stealth feeders, that they're not blasting around because they're just taking one squid at a time, like an owl at night coming in and on a bird, taking the birds without spooking the rest of them. So that's just my guess. But the main thing I'd like to say is that these guys are down there eating these things that we don't know anything about. These things that we don't know anything about are the things that are released by taking 91% of all the big predators. Plus all the incidental take of the things that they also ate them. So that engine, these fish and squid, are really important to these guys, and I predict that these guys have really important roles in that they are responding to some of these changes. But we don't know anything about the beaked whales. They're really interesting animals. They don't have teeth. The males have teeth, the beak, which they use for fighting. They apparently just come up to squid and suck them up, or fish, just suck, 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 suck. So they're not herders like the other ones. It's a whole different feeding guild that really needs to be some research. Let me just summarize and make the points I've been trying to make over and over again. These ecosystems are really complicated. We don't know much about the engine, as I call it, these little guys in the middle. We have to look at them, and to look at them, you have to have time series data. If we had Cal Coffee programs in all these controversial zones, we'd be a hell of a lot better off, because it's the only program that really does have the spatial scale and now the temporal scale. But we don't. So you've got to figure in all the physical oceanography. You've got to look at the climatology. In order to study these guys, you've got to have that big picture. The food chain connection, I haven't talked about enough, between the copepods and the euphausids, these little things, up to that next system. I don't know how that works. I don't have any guesses. I'm sure real oceanographers do, but I don't. And again, these are the guys that I think are the important players. The small herring-like fishes, especially the squids, and then in the future you're going to see more and more about jellies of various sorts. And finally, the roles of the marine mammals are poorly understood. They have all sorts of techniques that we really don't know much about, but that are really brilliant foraging tactics. They're neat animals, and they certainly need more study. And I think that the irony of this is that a lot of this research, most of the information that I know about for these bigger predators comes not from academe, but from the National Marine Fisheries Service. And it would be really neat, I think, to see oceanographic institutions going out and jumping into this quagmire of poorly understood systems. Okay, well that's my spiel. Thank you for your patience. The question was then, if I get you right, is how then, Dayton, would you, a diver, study the mesopelagic? And it's an unfair question. I'm out of my water, but I think you've got to have Cal Coffee type programs that look at the scale and get those animals, even the ones that are hard to get. You can study squid. There are some people that study them, You can catch them alive. But it's hard. And the payoff is slow, so you don't get tenure chasing squid around for 3 years, you know. But it can be done. It's just that we need to recognize that this is really important. And so that's what I would try to set up, sort of Cal Coffee analogs. They'd be different in different ecosystems, of course. And I would go after the hard questions instead of doing the easy things, which are easily studied but much less important. The question was about the jellyfish, and the ones that I had the picture were the Antarctic, and they don't have common names. I don't think you've seen them.
What in the world do they eat if they're just getting rid of so many things?
Well, I mean, they eat the copepods. They eat a lot of those smaller fish. I mean, those big jellyfish will eat a fish this big, but most of the jellyfish in the Arctic, I think, are species that are sort of maybe this big with tentacles that are 10 feet long at the most, and I think they're eating smaller things. I think that they are eating the copepods and the fish larvae, especially the fish larvae. I think that's where they're going to kick in their most important roles, is filtering out the fish larvae themselves as well as the food bases for the fish. The question has to do with the ctenophore in the Black Sea that was introduced, and it did basically take out everything. And my understanding of that story is that they finally have introduced, still another introduction, of course, a ctenophore predator, still another ctenophore too, that eats those filter-feeding ctenophores, and that predator now is all over the place, and that those things are gone, so that the system is coming back. But you know, once you start playing biological control like that, you know, you're asking for. It's a risky business, but at least it's probably saved the Black Sea. The question has to do with rephrasing it a little bit. Yes. You know, how do you separate out human impacts from natural impacts, and you know, how much of these changes in the ocean are human-induced versus climatological, say? And I think that, well, I can't give you an exact answer, but Cal Coffee can give you a pretty good picture. It shows these regime shifts, and sometimes, for example, the Pacific Decadal Oscillation seems to be helping the salmon recover. The regime shift seems to be coming back. The salmon are coming back. I don't want to downgrade the importance of these regime shifts and the climatological effects. They're very important, but so are taking out all of the great whales and 91% of the big fishes. And actually, I think that there are fairly good data, because people will always say, well, I mean, we aren't really the problem. The problem is climate. The problem is something else. But you know, I think that the Pew Oceans Commission report, for example, in my contribution to it, you know, documents a lot of reviews that show that human impacts are responsible for most of these oceanic problems. The regime shifts don't really cause collapses, they cause declines. And the animals are adapted to regime shifts through longevity. So the adults live for a long time so that they can live through a regime shift, and then they're there to reproduce again. The king crabs, for example. The regime shift happened in the mid-70s. There were a lot of big old king crabs. They would have lived till now, because they'll live for, you know, decades. And unfortunately, they were all fished out. And so now there's no king crabs left to bring it back, now that the regime shift has happened. So it's going to be hard. So both climate and human impacts are important, and it varies with the system. Kirk.
And variation is a natural.
There's a lot of natural. That's what that cartoon, the Stommel diagram, is trying to emphasize. Variation is the name of the game over large scales. Absolutely. The question was, I just assumed that you understood it and I didn't go into it. I'm sorry. What is Cal Coffee? Cal Coffee is a cooperative fisheries program that Scripps has contributed to, and National Marine Fisheries Service and the California Fish and Game, that started when the sardines crashed. And they actually spent several years fighting in the 50s on how to actually study the whole system. They did it right in the 50s. They had some of the best people in the world. They did it right. They surveyed the right area, the right grid size, and so they're regular transect lines that go in and out across the California current. They're taken regularly, and they've been doing it every year since the 50s. Now, budget constrictions have pushed it down and reduced a lot of the cruises, but they're trying desperately to keep it going. It's going to be nip and tuck to see whether Cal Coffee survives the next few years. But it is the only program of its sort in the world. It's unique, and it's something that California should be horribly proud of and very protective of, and yet nobody seems to be saying goodbye.
They're quarterly surveys. They go 4 times.
Yeah, well, they're quarterly now, but sometimes they vary them. I mean, the management of the surveys, there's management teams that work on it, and it varies a little bit, but that's the essence of it. Well, I mean, I may be wrong on that. I don't know. They certainly go below the thermocline. And those people that are down there hiding out below the thermocline are also people that use much less oxygen. And so if I'm hiding from some of these guys, and if the oxygen minimum zone is within reach, in many cases it's too deep, but if it's within reach, I might just go down there and hold out until night, and then I come back up, because I'm a lot safer, because those big fish need a lot of oxygen. They're not going to go into that oxygen minimum zone. And so, if I'm one of them, I'd go up there. But I think most of it, the literature shows, is the thermocline. I just have this feeling that the oxygen minimum zone is still another important refuge, and I'll bet those beaked whales are playing with it, because they don't care about the oxygen. They're air breathers. Well, I mean, I know that in the last year or so, some of the wild salmon the salmon have all sorts of other problems from introduced fish and salmon and things, but there's a salmon and a National Academy Committee looking at salmon, and and they were looking at all these various things, and then the PDO happened, the oscillation shifted. Wow, there's a big year class coming back, and the Alaskan fishermen can't even get any money for their salmon, and it's just a correlation. Yeah, it's just a correlation. I don't know much about salmon at all. Good to eat. Okay, thank you very much.